Moving into 1.6, we're going to look at combining functions using operations, and then we're going to introduce an idea of something called a composite function. In combining functions, we're really just going to use some of the operations that we're familiar with. In essence, we're just going to be finding their sum, so adding them, subtracting them, finding their difference, taking their product, or dividing them, finding the quotient. And really what we have to get used to is some of the notational ways that we write this out. When we find their sum, we could say what we're doing is taking or finding the f plus g of x. Remembering again that the x here in function notation doesn't mean multiply. It's saying here that we're adding them together, and it's of the x there. And all this means is we're going to take the two functions and add or subtract them if we're finding their difference, multiply them. A couple different ways. With the multiplication, we can put that in parentheses, or we don't necessarily have to put that in parentheses. But we do follow the order that we have. And that's the same with division here. The f of g of, I don't know why there's a c there, but that should be an x, equals f of x over g of x. I think that's a typo right there, so just ignore that. At any rate, the domain of each of these functions consists of all the values of x, which are common to the domains of f and g. For most of these, just like with all functions, most of them will have a domain of all real numbers. But we do have those exceptions, right? We can either have we can't have zeros in denominators. So if we ever have a denominator, we have to look for that. Also, we cannot have negatives under square roots. So f, this is the division symbol there, f over g for all x, of course, g of x, which is in the denominator here, equal to 0 must be excluded. So nothing really new there. We'll get to the domain there, those more difficult ones, in a bit. But first, let's look at combining functions with two just given functions that we have here. Here we have a quadratic, and then we have a linear. And we're going to find the subtraction when we have a number, and then f over g, and a specific input. And then we're going to look at just if we have x, right? Basically, if there's just an x there, we're going to be coming up with a new function, as we'll look at how to do that. So let's start off with some more basic ones where we actually have a number. So you could do, when I have an f minus g or an f plus g of a specific number, or we have f over g, I just like to kind of follow the same path here, but we can do it separately and then just find their difference. In other words, plug 4 into the first one, find f of 4, get that result, and then find g of 4, get that result, and then subtract the two numbers. So that's one way to do it as well. That's the nice part about having an actual value that we're plugging into 4. But to keep it consistent, so that we're always doing the same thing, you can also just write out the subtraction of f of x here, subtracting g of x, and then start substituting. One thing I do want to point out is that if you have a subtraction here, it's imperative that we put these brackets so that you remember that we're subtracting the function, the whole function, not just the first term, but the first term, the second term. If there's more than that, you just want to make sure we're subtracting each term. So in other words, we're going to distribute a -1, so we'll make that the opposite, or the negative parentheses, and then plus 2. Once you have the plus there and you've distributed that negative, then the brackets aren't really necessary anymore. All right, then we can substitute the 4, and we start working this out. So 4 squared is 16, and then 16 minus 24 6 times 4, plus 8. And then we have plus negative 4, and then plus 2. And we start combining these together. 16 minus 24, that's negative 8. And we have negative 8 plus 8. Well, that's becomes 0. Then we have plus negative 4 plus 2. So that's negative 2. So we see that the f minus g of 4 is equal to negative 2. Same thing on the bottom. I've got the same two functions. We have the top function, f of x over g of x. And we're substituting 3. So let's get 3 in there and then just work this thing out. That's 9 minus 18 plus 8 over 3 minus 2. Well, let's just go ahead and do that one. We know it's 1. 9 minus 18 is negative 9. And that gives me negative 9 plus 8. Negative 9 plus 8 is negative 1. So we have negative 1 over 1 or negative 1. Remember, in a fraction, if the top is negative and the bottom's positive, we have a negative outcome. Same if it's positive on top or negative on bottom at the same time, then you're also going to have a negative. Different signs give us a negative outcome. Going on to the next part, we're actually going to do the, we're going to find the f plus g of x. There's a little typo there, so I fixed that, but there's supposed to be an x there. And so now we're just going to look at these as being two functions that we're combining. In other words, we're going to look at this and really just do some combining of like terms. When we're adding, again, I put the brackets here, but we don't necessarily need the brackets, because if you distribute a positive, right, think of that as positive 1, well, 1 times anything is still equal to itself. So the brackets aren't necessary, but I'm just trying to do the similar things here just to get in good habits. So really what we have is x squared minus 6x plus 8, f of x, plus x minus 2. And so we want to look to and combine like terms. Like terms have the same variables being raised to the same powers. Well, that's pretty straightforward. There's no other x squared, so we keep that as x squared. And then as I look through here, I find any other terms that have just x to the first power. We have a minus, and you have to remember to pay attention to the sign out front, so that's a negative 6x plus x. So negative 6 plus 1, that's negative 5x. 6 negatives plus 1 positive leaves me with 5 negatives. And then we have positive 8 and minus 2, so that's plus 6. And so the f plus g of x, the sum of f and g, is x squared minus 5x plus 6. Same thing here. I'm just putting in the x. Since I copied and pasted these, they just kind of stayed the same. So we don't even have to leave them as blank spots. You know, it's just the f of x subtracting the g of x. But now I do have this negative here that I want to distribute. So that's going to be a negative x and then a plus 2. If we think of that as a plus. Once we have a plus there between the two brackets, we can ignore the brackets. So x squared minus 6x plus 8, f of x. Notice that didn't change at all. And then we have subtracting x and then plus 2. So very similar, in a similar way, we have, well, x squared by itself, but now we have a minus 6x minus x. Instead of negative 5x, that's going to be minus 7x. And we have a positive 8, positive 2, so that's plus 10. So that is the difference of f and g of x. Moving on, we're going to take the product and the quotient then for our last two. So I'm going to put the x's in there again. And so it looks similar. Again, I just copied and pasted these. So there's no need to put parentheses and then put the x. You can just rewrite them. But now we want to multiply them. And so what we have here is a binomial times a trinomial, 3-termed equation with a 2-termed equation. And so we're going to take those expressions and multiply them. And when we do something like this, it's kind of that whole FOIL approach. It's the idea, except that one has three different things. So we have to take x squared and multiply it by the x and the minus 2. Then the minus 6, we have to do that same thing. We're going to distribute it to the two terms. And then the 8 also gets distributed to the two terms. So starting on with x squared, that's x squared times x, or x cubed. Then we have x squared times the minus 2, so minus 2x squared. Then we go to our 6x minus 6x times positive x. So that's minus 6x squared. Then we have minus 6x times minus 2, so plus, so minus 6 minus 2 is plus 12x. And then we have positive 8 times x, so plus 8x. And then positive 8 times minus 2, so minus 16. And yeah, so every term in the first bracket or parenthesis got multiplied by every term in the second bracket or parenthesis. That gives us a sum total of 3 terms times 2 terms, which is 6 multiplications. And you can see we ended up with 6 terms here. But then we want to combine any like terms that I have. And so we don't have any other x cubes, so that remains. We have a couple x squareds, minus 2x squared, minus 6x squared, so that's minus 8x squared. And then we have plus 12x plus 8x, so that's plus 20x. And then we have minus 16. And pretty much that's, combining all our like terms, what we found is the product of f and g of x. Let's go ahead and go down to this last one. We're going to find the quotient now of the two. And really what we have to do here, whenever we have more than one term on the bottom, we want to see if anything can cancel out. In a division, we're always looking for things to kind of go into the bottom. But since we have a binomial, things to go into the top, sorry. But what we have on the bottom is x minus 2. So we would need not negative 2 or x individually to go into things on top. We actually, in order to divide this into the top, we'd have to have another binomial that is x minus 2. And so if it was just x by itself, we could take x into each of the terms above, or negative 2 we could take into each term above. But with a binomial, you got to be able to take that whole expression into what's above. So what we have to do is to factor the top and see if we end up with something similar. In other words, we need to look at it as a product and see if one of those factors, one of the portions of that product, is indeed x minus 2. So x and x give me x squared. So now I start with that. I have a positive 8 here, so I know that the product of the two numbers I pick needs to come out to 8. But more than that, it needs to come out to a positive 8. So that means we have to have matching signs, either 2 positives or 2 negatives. Since this is a negative sum, right? A negative sum of minus 6, I know that the two numbers have to be minus. And 2 and 4 give me 8, and negative 2 plus negative 4 give me negative 6. So there we have it, and we see that x minus 2 is actually one of the factors. And so with that, the x minus 2 can cancel itself out. And so we do end up with a simplified function here. Otherwise, we would have just, if we can't cancel anything, we just have what we have on the left. And you could write it either as the trinomial that we have it here, or you could leave it as the product. So you leave it in terms of its factored version. Either way, this is your new function, x minus 4. So the quotient is x minus 4. However, since the original function had an x minus 2, this is its simplified version, but because the original function actually had this denominator value, we would have to say x minus 4 where x is not equal to 2. We still have to limit at the domain of the original function since x minus 2 was not or could not have 2 plugged into it because it would give us a 0 in the denominator. So we still have to limit the domain based on making sure that it's never equal to 0. We're going to take a look at something that's probably new to you. It's called a composition of functions, where we have two functions just like before. The composition of function f with function g is written as f of g. And it's defined as f of g of x. Now, notice that I'm saying f of, just like we say with functions. And in fact, like usually we say f of x, right? So if I'm saying f of g of x, what we're actually saying is that we're plugging in a function into a function. So literally, that is what we're doing. We're taking the f of g of x. So g of x becomes, or the other function becomes, my input. So I actually like, these are two different ways of writing the composition of function. Over here, it's a little more simplified in terms of it, the way it looks, but that hollow circle there indicates that you have a composite function, not just a product, right? With the multiplication, we kind of have just a dot. This is a hollow dot, so that differentiates it a little bit. This is a little more descriptive in its notation because we actually see the g of x being plugged into the f of x. But I do want to point out that the order here, it's like x is being plugged into g, which is then being plugged into x. So it kind of follows this flow with the x over here going into the g, which is then going into the f. And anyway, so that's kind of the way you want to think of it when you run into that notation. But another way that you can describe it or talk about it is to say, as we see down here, the f of g of x as f composed with g of x, and f of g of x as f of g of x. That's how I like to say it. But the domain of f of g of x consists of all the variables in x that are in the domain of g, for which g of x also is in the domain of f. So we actually have to look at both domains there, starting with the one that gets plugged into the other. So in f of g of x, we start with the domain of g, and then once we have actually done the substitution into f, then we have to look at the domain of f as well. Any values that we're leaving out of one, we also look at the values of the other. We have to leave them both out. So thinking we had in a picture wise, we have the domain of f of g of x here, but this domain matches what also is in the domain of g of x, right? So what we're allowed to plug in to g, and then since this becomes the new domain for f, we have to also look at that. So whatever also we can plug into f, which is this group here, becomes part of my domain as well. And that becomes the overall domain of the whole thing. When we find the f of g of x, we're actually coming up with a brand new, unique function. So it's a new function that's kind of a combination of both the f and the g of x. So with, let's just take f and g, these two here, we're going to do just one plugging in of, doing it with the numbers. And we're going to do them in different orders and see what we can come up with. The f of g of 1, the g of f of 1, and the f of f. We can even have a function be a function of itself. And so let's see what happens. Let's start with the first one here, the f of g of 1 to another one. 1 gets substituted into g, and then we'll take that result, and that gets substituted into f. So first of all, let's just find the g of 1. The g of 1 is 1 plus 1. So very simple. So that's 2. So now 2 becomes the input for f of x. So 2 gets substituted in there. And so 2 cubed is 8. So the f of g of 1, notice we put parentheses around both, is equal to 8. Let's do it or let's see what happens if I reverse it. So 1's going to get plugged into f, which will then get plugged into g. So we'll start off with finding the f of 1. Well, that's 1 cubed, which is still just equal to 1. Oops. And so then 1 gets substituted into my g of x, which g of x is made up of x plus 1. So we see that 1 plus 1 is 2. So the g of f of 1 is equal to 2. Fairly simple idea here. Let's try this with negative 1. So we're going to take, whoops, there's that line again. We're going to take negative 1 and plug it in for f. So we're going to find the f of negative 1, which that is negative 1 cubed. Well, negative 1 cubed is actually still equal to negative 1. It's negative 1 times itself 3 times, right? So this becomes positive 1, and then we still have this last negative 1 here. And so we still end up with a negative 1. So then that's going to become my f again of that output, becomes my new input. And we end up with negative 1 cubed again, so negative 1. So the f of negative 1 is negative 1. I want to make sure that looks like a hollow dot there, not a solid dot. Solid dot would indicate we're actually going to multiply. Two very different things. What about just coming up with the functions, right? So in other words, keeping it as x and not specifying an input. What does that look like? How do we do that? Well, it's simply, as you guys know, it's just going to be some substitution that we do. So we've changed up our functions here, and we're going to do the same 3 different ways here. So let's start off with the f of g of x. I like to write this as f of g of x, just like we do with numbers, like finding the f of negative 1, putting that in there. So in other words, I want to take f. Let's rewrite f. F is 2x plus 1, so I'm going to go 2, give a much wider parenthesis there, plus 1. So 2 times x plus 1. But then my x is this function g of x, and g of x is equal to x squared minus 3. So I'm going to put in x squared minus 3. So we took out the x, and we put in the expression g of x, and now we just have to simplify it. So I'll distribute the 2, so that's 2x squared minus 6 plus 1. Combine my like terms, 2x squared minus 5. Negative 6 plus 1 is minus 5, so 2x squared minus 5. What about the g? So if I reverse that, and I found the g of f of x, right? So x goes into f, and then f goes into g. So now f is my input. That's x squared minus 3 is g of x. And then here we're going to input the f of x, and we know that f of x is 2x plus 1. So what I want to do is I want to square 2x plus 1. So that's 2x plus 1 times itself. Now we're going to be subtracting 3. So again, the more you can write this out as you're carrying it out, 2x times 2x is 4x squared. 2x times 1 is just 2x. Then 1 times 2x again. And then 1 times 1, that's plus 1. Then we have the minus 3, so don't forget that. Easy to kind of leave that off to the side eventually and forget about it. But 2x plus 2x is 4x. And then we have plus 1 minus 3. That combines to give us minus 2. So there's our function. The g of f of x is equal to 4x squared plus 4x minus 2. And now lastly, we'll find the f of x. So that's the f of x. Kind of weird to say. But we know f of x is 2x plus 1, so we'll go 2 parentheses plus 1. And then into the parentheses, we put our function of itself, 2x plus 1. Distributing the 2, that gives me 4x plus 2 plus 1. So that's 4x plus 3. And I just got plus 3 with the plus 2 and plus 1. That's pretty much it. That's my composite function there, f of x. Now we're going to look at how to find the domain of a composite function, which of course is going to be made up of a combination of what our input function is, along with the resulting f of g of x function, or your composite function when you're finished. So when we're starting to look at the domain, we first want to examine what the domain is of not the f of x function, but rather the g of x, because g of x is what is being substituted into f of x, and it's going to change f of x. So, but the one that is being plugged in this case, x is first attached to g, and then g of x is going to be the next domain of f. We need to look at what the domain is for our original function that we're going to plug in, g of x, because it itself is being put into the f of x. So here we look at this and we can say, okay, well, x plus 1, for it not being able to be 0, we'd see that x cannot be negative 1. Subtracting 1 to the other side would show us that. So I already know that this is going to be part of the overall domain, but now we need to actually do that substitution to see what the resulting equation is going to be. So we're going to find the f of g of x, which is going to be 2 over x, which is a fraction itself, 5 over x plus 1. I know some of you are already not liking this. Yeah, that's pretty normal. So now what we need to do is to go ahead and combine these terms that we have here. So looking at, I'm just going to hone in my focus here. We're first going to just simplify this, and then we'll look at what values for x are going to be problematic. Okay, so focusing on that, I'm just going to over to the side here, do 5 over x plus 1 minus, now what I want is 3, but I want 3 with the same denominator as what I have there. So I can put in x plus 1 as long as I put it both into the top and the bottom of that, right? X plus 1, that would cancel, and it would just leave me with 3. So these are two equivalent expressions, equivalent fractions there. However, let's make this plus negative 3. Let's simplify what we have there on the top. So I have 5 plus negative 3x minus 3 all over x plus 1. notice how for the denominator of my fraction there, we now have this fraction. So I have 2 divided by 5 minus 3x minus 3. And let's go ahead and simplify that, sorry. Let's put the 5 and the minus 3 together, and just anytime we can simplify it, we like that. So we're just going to rewrite that. So it is negative 3x, and then 5 and negative 3 is positive 2, so I'm going to put plus 2 over x plus 1. Okay, so we have 2 divided by this fraction down here. We don't like to have fractions within fractions, so here we realize that this is 2, and then my fraction bar is a division symbol, right? And so let's just go ahead and divide here. If I divide by negative 3x plus 2 over x plus 1, this is the same as multiplying by its reciprocal. So it's the same as going 2 times the reciprocal, which moves the x plus 1 over negative 3x plus 2. And we need to remember that we want to distribute that 2 to both terms on top, so that's 2x plus 2 over negative 3x plus 2. So this is the simplified version of this whole thing over here. So we've simplified it, right? We substituted, and then we combined and we added, and we got a common denominator, yada, 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 and then we simplified it. So the composite function, f of g of x, is this. What we don't want to have, again, in the domain is any values of x that would result in a 0. So I need to hone in on this function here, the bottom part, the denominator there, negative 3x plus 2. And I want to say what values for x are going to result in 0. I want to eliminate those. So subtracting 2, we see negative 3x equals negative 2. Divide both sides by negative 3. I'm kind of crowding out my screen here. We end up with x equal to negative 2 over negative 3, so that's actually positive 2/3. So x cannot equal 2/3, as well as negative 1. So here was my original g of x restriction. Here was my f of g of x restriction. Can't be 2/3. And so the intersection of those is we don't include 1, so a and b, and we don't include 2/3. All of the other numbers are okay. Let me see if they, no, okay. So let's write this out in interval notation. When we exclude certain numbers, interval notation can be a little awkward. So one way to express the domain here, we have 2 methods, right? One of them is simply to describe it. So we would say x such that x is a real number, but x cannot equal negative 1, and x cannot equal negative 2/3, or you could just list those 2 numbers with 1 not equal to, right? X not equal to negative 1 and 2/3. The other way to put it in interval notation is we want to describe the blue line that we're seeing there, starting from left to right. So we would just say negative infinity, always parenthesis with that, up to negative 1, and we use parenthesis because we don't want to include it. And then we say in union with, so we put a u there. And then now we're going to go from negative 1, not including negative 1, up to 2/3, not including 2/3, right? So we're literally describing the blue line with these breaks in it. The not equal to is shown with a parenthesis by those numbers. And then, of course, we start up again, going from 2/3 all the way to positive infinity. That's how we can show the domain here of this composite function in both interval and set notation.
It can also be helpful for us to redefine a function, kind of break it apart as a description of two functions that are compositions of each other. You may say, why would we do this? Like, what is going to be the point of this? This actually comes in handy in calculus. So this is pre-calculus. We're just going to practice this kind of idea here. And we don't take it as far as we will eventually. But it's good to know that this is something that we can do and that it's fairly simple to do. Looking at this, that there's things like when we raise things to powers that are kind of a big deal, right? Those will change graphs, right? Something raised to the 1/2 power, which is what a square root really is, it's the same as raising it to the 1/2 power. When we raise things, for example, to the 2nd power, we see that we get the particular graph, we get a parabola, right? And things raised to the 1/2 power or the square root, they have their own graphs as well. So to kind of look within there, we can see that one way we could kind of break this apart and write it as the function of two other functions is we see, okay, well, we've got the square root here. Why don't we just take the expression under there and make that its own function? So we say, let's say g of x is equal to 2x squared plus 1. So I'm setting this as its own function, its own quadratic function. Then we want to describe f of x as what's kind of left there, right, with x. And if I just take that out, but eventually want to substitute it back in a composition function, we would write f of x as being 1 over the square root of x. Okay. And remembering that when we do the f of g of x, so f of g of x, that we start off putting x in for g, and then that g goes into f. So if this is my function here, g of x, if I found the f of g of x, I would be plugging that into 1 over my square root of x, right? So we write out what the x is, and now the g goes into that, and my g is the 2x squared plus 1. So that takes me back to this original function, h of x. This is called decomposing a function, right? We first look for something that is kind of keeping in mind our g of x, is something that we're going to plug into the other function. And so we say, okay, well, if I take this longer expression and just kind of make that a separate function eventually, and then define the other whatever's kind of left over there, again, x being in the place of what we replaced, now I could express that same h of x function as a composition of two functions, f and g. One nice thing about composition of functions, as opposed to one big function that encompasses everything, is that in a story problem, sometimes there are multiple layers to what we're doing. So in a situation where x is really representing multiple layers of a overall something we're trying to figure out, right? A bigger problem. We can kind of express it in steps where each function is like a step in that process. And then we can bring it together. So looking at just an example here where there's two different things that are going on. First of all, we have a discount that's being offered by a manufacturer. And then we also have a discount that's being offered by the maker of the vehicle. So the car dealership is offering a discount, but then the manufacturer is also offering a discount. So the car dealer is offering, maybe hey, 8% off today, right? So they're going to offer an 8% discount off the manufacturer's suggested retail price, MSRP, of, I feel like one of those commercials, right? MSRP, of X dollars for any new car on his lot. At the same time, the manufacturer is just offering a $4,000 rebate for each purchase of a car. So you're going to get $4,000 cold hard cash. Basically, they've created a loan for you. But we all like getting nice little cash in our pocket. So it's a bit of a trick, just so you know. First part, they say, let's write a function Rx that represents the price of the rebate. So there's two different layers here. We have the percentage discount, and then we have a rebate, right? And they're both coming off the price of my car. So we need to try to figure out a function that's going to represent both those things at the same time so that we can get both of our discounts. So you can see how that's kind of a two-stepper. Regardless, we're going to first do a rebate one, so we're calling that R of X, and then a discount one, D of X. And then we're going to go two different composite functions, R of D of X and then D of R of X, because that 8% plays a role. Percentages are always based on something, right? Percent of something. So are we basing it on the MSRP, or are we basing it on after the rebate, right? So all of those things are going to make a difference. And then we're going to do another thing there at the end. So let's just start with the first. Let's try to do a R of X, where R of X represents the price after a rebate. So the rebate is just that $4,000 that we get back. So we're going to say X is representing price of the car. And so we're thinking the original price of the car, right? MSRP. And that's what our percent discount is going to be represented on here. But first, we're just doing rebate, right? So R of X, we can say, is equal to the price of my car minus $4,000. Pretty simple. Price of my car after the rebate. All right, B, we're going to write a function that represents the price after the dealer's discount. So D of X is going to be my car price minus, we're taking 8% off, right? So we want to figure in 8% or 0.08 times X. We don't like to have the percentage symbol in there, so we need to be able to know that 8% is equal to 8 out of 100, which is 0.08, 8 100ths. We divide by 100, so there's two zeros, move that decimal back, which is after the 8, 2 spots. So our original price minus 8% of the price, which actually we can combine these together. These are like terms. 1 minus 0.08 is 0.92, so we're going to 0.92 of X. Now let's move over to our composition functions. R of D of X, and then we're going to do D of R of X, and talk about what they represent. So here we're doing X, D of X, and then we're going to put that into R of X. So we're going to find the R of D of X. D of X, remember, is the discount. So that's doing the discount, the 8% discount, and then the rebate. So R D of X, if you remember, D of X was equal to 0.92X. So 0.92X. And so plugging that into R, I'm going to go ahead and write these up here just so we have them. R of X was equal to X minus 4,000. And D of X we found was 0.92X. So this would be plugging that in for X, 0.92X minus 4,000. So that is my, just so we have both things written here, R of D of X. That's the first thing. Now we want to find the other one. So this is X into R and then R into D. So we're finding the D of R of X. So the D of R of X, oh, I just rewrote the same thing. Let's not do that. We don't need to be repetitive here. But I want to think about the D, which is 0.92. So this is 0.92 multiplied by my R, which is X minus 4,000. Distributing that out, that gives me 0.92X minus 0.92 times 4,000, which is, if we multiply those things, 3,680, so $3,680. And this is my D of R of X. What do they represent, right? What's the difference between these two? Are these equivalent? Well, we see that they're not. Here we're subtracting 4,000, and here it's the same product, but then we're only subtracting 3,680. This is this first one represents doing the discount first, so taking the discount off of the RS, whatever that was, I don't remember, the MSRP, and then doing the rebate after that. So we're doing the discount first, then we're doing the rebate. Here we're doing the rebate first, and then we're applying the discount. With the rebate, that means we've taken money off of the price, and then my discount is coming after that. And so the last thing that they asked us to find is the difference between those two things. In other words, take the R of X, so the D of R of X. So this was, my D of R of X. What was that function? That was doing the rebate first. So that was 0.92x and then minus 4,000. Let me go back and make sure that was right. So the R of D of X, is that what we have there first? No, I'm sorry. The first one is D of R of X. That was the second one here. So I have that backwards. This one's doing the rebate first and then the discount. So that's 0.92 minus 38 or 3680. Let me make sure that's correct. Yep. And then from that, we're going to subtract the R of D of X, which is 0.92 minus 4,000. This is not anything there. Well, before we get rid of this, we're subtracting, so I want to distribute that negative to both. So we made the first one was positive, becomes negative, second becomes plus 4,000. Now we can ignore or take out the parentheses. Sorry, I forgot to put the x's in here. That's 0.92x for both of those. Well, that's positive 0.92. I said this was just a thing out here, so ignore that. It's not negative. We had that and then a negative, so that becomes 0. But then we have this is negative plus 4,000. That's basically subtracting those two. And if I subtract 4,000 and 3680, we get 320. So what's the lesson? What is this telling us? What this is telling us is, as far as the price of the car goes, when it comes to the price, the overall price that we're going to pay for the car, if I take my rebate first and then the discount, the price of the car is going to be $320 more than if I took the discount and then followed it by the rebate. So the price of the car, no matter what the price is, remember X is just a general thing, and all these things are representing that. X is just a general price. It could be any price. No matter what we do, if we took the rebate first and the discount second, we're going to pay $300 more. The price will be $320 more than if we took the discount and then the rebate second. So which one of the two was better? Well, it's easier to kind of see back here, but a higher price is not a good thing, right? So this is actually going to get us a better deal, this first one, because we're going to take the discount first, then we're going to get that $4,000 back. If we do the rebate first and then do the discount, we end up saving less, so we end up paying more. We subtract a smaller amount than 4,000. So you kind of have to think about that in terms of what is X representing, what are we finding, and then what is our composition telling us. And if we're talking about the price of a car, lower prices are better, and we end up getting lower prices if we took the rebate first. The discount first and then the rebate. That concludes our section for today.